Okay, so in 10.3, we're going to cover the dot product. Most students should find this is somewhat familiar. You probably worked with this in a physics class or possibly another math class. So the dot product itself is a pretty simple calculation. We'll take two vectors, in this case u and v, with components u1, u2, u3, and the same for v, just generic components. Dot product of these two vectors, u dotted with v, is u1 times v1, so the first component times first component, second component times second component, third component times third component, and sum all of these up. So something like that. Pretty straightforward calculation. One thing that you should note is the operation is binary between two vectors. So we take two vectors, combine them in some way, the result is a scalar, a single number, a real number. Okay, vector versus scalar. So we convert two vectors into a scalar number. It's really important to pay attention to what species things are now, what types of objects we're seeing as we do these combinations of things. So for our first example, they ask us to find the dot product of two given vectors. So we have 3, 8, 2 dotted with -5, 2, -1. Here we see the first components, 3 times -5 plus 8 times 2 plus 2 times -1. And carried out these products. We have -15 plus 16 minus 2, and ultimately we end up with -1, adding all those numbers together. So pretty straightforward. Once you practice this a couple times, it's pretty much impossible to forget. So that's the dot product in its most basic form. Now, what can we do with the dot product? It's quite a bit, actually. So it's got a lot of nice properties. So one of the first things we'll do is prove at least one of these properties, maybe two. And we're just going to assume that we have two-dimensional vectors, 2D vectors, u, v, and w. Well, if we need w, that'll come up. And a scalar c for the properties that follow. So in other words, three generic vectors and a generic scalar c. A scalar, again, is a real number. So two-dimensional vectors, just to kind of keep things simple here. So all of these proofs carry over to 3 dimensions. So we keep that in mind, and you can prove this for 3-dimensional vectors as well. You just have to write in an extra component and be careful with that. Okay, to prove part A, u dot u is equal to the magnitude of u squared for the vector u. Well, with any identity, if we're going to prove this, well, we start with one side or the other. So we're going to start with the left-hand side, u dot u. Well, then we'll instantiate components for this vector. Well, what better than to call the first entry of u, u1, the second entry of u, u2. Nice generic names. Those could be any real numbers, so that this property holds for all vectors. Once we're done with it, u dot u is this vector dotted with this vector. If we carry out that dot product, it's u1 times u1 plus u2 times u2. Well, those are two numbers that are equal to each other times each other. So we have u1 squared, u2 squared, and that is the square root of the square of the square root of this. So in other words, this square root and this square cancels out, and we get what's above. But if we write it this way, we realize that this line right here is actually the magnitude of u, but squared. Okay? And thus the proof's complete. We started with the left-hand side, ended at the right-hand side, and that's an end of proof symbol. So the demonstration is complete. Okay, so we have some more properties here. I'll leave some of these as exercise, but they're going to follow very much in the same way. You write down one side, work out some calculations, arrive at the other side. Okay, just like a trigonometric identity, only no trig involved in any of the ones on this page. Now, I've set you up for part C just because W shows up as well, and it looks like we're starting with the left-hand side here. And we instantiate values for u. u1, u2 to give it a specific name, just like above. Same for v, same for w. And from here, it's just vector properties. We can distribute, or we can add these two vectors up to get v1 plus w1, comma v2 plus w2. That's a new vector. Then you can carry out the dot product with this vector, and hopefully you arrive at what's on the right-hand side. I'll leave a lot of the adventure there to the reader, to the students. Okay, at the very bottom, we've got one involving 0. So another nice quick result we can get. So we'll start with the left-hand side. The vector 0 times the vector u. Well, 0 is the vector with all zeros as its components, obviously, and dotted with u1, u2. Well, we see pretty quickly 0 times u1 plus 0 times u2. We arrive at a scalar value of 0. Not a vector value of 0, but a scalar value of 0. Good, and that's the end of that demonstration. So the proofs for these properties aren't too difficult once you know how to start them and instantiate these vectors, sort of how I laid you out here. Then the rest is just a matter of using known vector properties to carry these proofs out. Nice little exercises, easy environments to prove things. Okay, so maybe a bit more of a complicated theorem to prove is the following. This is a nice characterization, very useful characterization of the dot product. Now, if theta is the angle between the vectors u and v, then we'll have the following relationship. U dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta, the angle between these two vectors. All right, so where does that formula come from? Well, it actually comes from the law of cosines. Okay, and as the example below kind of hints, we'll use the law of cosines to prove this vector identity. Okay, it's really useful vector identity because a lot of times we want to know if two vectors u and v are perpendicular, and well, there's going to be a sign for that. We'll see that in the next page. For now, let's get this identity established. We can at least find the angle between the two vectors u and v with a formula like this, and maybe a few other things too. Okay, so the first thing to do is this. Let's draw arbitrarily u and v with coinciding terminal points. That's this picture right here, u and v drawn, and we know that the angle between them is theta. We've added another side to this to complete a triangle. We know that this is the vector u minus v, if you remember how vector differences work. So it's a nice key piece of information in this problem. Now, that's the vector diagram for it. Let's move on to the triangle, or the magnitude or lengths version of this. So in other words, just what's going on in terms of this triangle. Well, the length of this side is the magnitude of u, and similarly, this one's the magnitude of v, and over here we have the magnitude of u minus v. Well, we remember the law of cosines tells us that u squared, or this magnitude squared, plus this length squared, plus 2 times this length squared plus this length squared minus 2 length of u times length of v cosine theta, right? That's all equal to this opposite side squared. So this is our c squared that we might have known in the past, okay, in trigonometry. So again, just to make a note of things, what we're relating is this side to these two sides through the law of triangles, or law of cosines. Right, so moving forward with it, what this equation right here gives us is quite a bit to work with. And mostly we're going to work with that left-hand side and expand u minus v, the magnitude of that vector. So remember that subtracting one vector from another results in another vector. So u minus v is its own vector. And when we carry out these operations algebraically, we'll get some things that match up with what's on the right-hand side. So the first step is to rewrite u minus v magnitude squared as, remember that the magnitude of a vector squared is the dot product of that vector with itself. In other words, if I go off to the side here and remind us of this formula, u magnitude squared is the same as u dot u. We proved that on the previous page, or we at least saw that on the previous page. The properties of vectors. So call it property 1. Property 1. That's good to have around, and that's exactly what we're doing when we expand this. That's coming from here. So we get this written down. We'll subtract these two lengths squared over to the left-hand side, leaving this all by itself. And we won't touch the right-hand side for a few moves. And as we work our way down this, we will expand u minus v dot u minus v, and we're essentially foiling at this point. We have u dot u, we have u dot negative v, and so on as we move through this until we end at v dot v. Now, u dot u minus u dot u and minus v dot v are these two pieces, and the right-hand side is still the same. So we notice now u dot u minus u dot u, v dot v minus v dot v, those all add to 0. The only thing that survives on the left-hand side of these two terms, well, which you'll prove in the second property on the previous page, is that v dot u is the same as u dot v. So we commute those, in other words, swap their roles, and we end up with negative 2 u dot v is equal to negative 2 times this stuff on the right-hand side. Divide both sides by negative 2, and we end up at exactly the identity we were hoping to prove. That's a fairly complicated proof. Chances are you'd never be responsible for putting something like this together on a quiz or an exam, but if you can do this, you've got a pretty deep understanding of this material. Also, well, you know, if you ever forget the formula, then you can build it. So it's a nice thing to have in your back pocket. Okay, so moving on, corollary to this, and perhaps what explains what's so useful about the situation, well, not every time, not perpendicularity yet. This is just essentially we've taken the formula of the previous page and said u dot v is magnitude u times magnitude v cosine theta. And all we did was divide by magnitude u times magnitude v on both sides. That's how we arrive at this formula. There's not a whole lot going on in this corollary, but nonetheless, we'll use this formula real quick. So this will help us find the angle between two vectors if we ever wanted to do that. So there's just one step further along that path. So we're given two vectors and we're asked to find the angle between them. So this will be one vector dotted with the other vector divided by the magnitude of one vector times the magnitude of the other vector. Okay, all that's set up. I think we can all handle that. What we come out to is cosine theta is equal to 8 over 21 root 2. On the steps in here, we had root 98, root 9 on the bottom, so that was 3, root 98. Root 98 simplifies to 7 root 2 because it's 49 times 2. And that's how we end up with this expression in the very end. To solve for theta, take cosine inverse of both sides of this equation, and theta is equal to cosine inverse of 8 over 21 root 2. So pretty straightforward, we just need cosine inverse. And mathematically, that's perfectly fine. This is an exact answer. If they want this thing as a decimal rounded to a few places, of course, follow those instructions. Make sure your calculator's in degree mode if it needs to be in degrees, radian mode if it needs to be in radians. Otherwise, that should not trouble you too much. Okay, now perpendicularity. That's one of the most useful things of let's see.